I only see about 8 people here so far, so I'm kind of dawdling about this. I bought a new webcam and I suddenly realized it makes me look like I've been blue shifted, which is really strange because I don't have a webcam built into my computer, but actually neither does my daughter. So I bought a new webcam and I took the new one. So she has my old one. Yeah, no, I'm like, need to figure out if I just the
I was gonna say you do look a little blue, but I didn't know if you had a blue light in front of
no, I still, it's like I have sometimes I have the light turned on only in the corner. What? Oh, you have the old one. Oh, okay, that's fine. No, apparently, see, my husband is doing seminars from home this week, as opposed to going to Vegas, because nobody's going to Vegas right at the moment. He's doing Autodesk University. If those of you are familiar with AutoCAD, this massive 3D modeling drawing program that shipyards, architects, engineers, lots of people use it. That's apparently going on this week. So he's zooming from home. So he apparently is the one who has the other webcam right at the moment. While I'm kind of waiting for everybody else to show up, on Thursday, I am traveling. I have to go see one of my specialist doctors in the DC area. I'm going to try to Zoom from the hotel room, and I'll probably repeat this again at the end in case other people log in. If it takes me a little while to log into the system and get it going, I mean, they have Wi-Fi, it's a hotel. But if it takes me a little while to get logged in and get it all going from the hotel, just kind of be aware that that might be the problem. I don't anticipate not being able to do it, but just fair warning. I mean, hotels usually have decent Wi-Fi, but these days everybody's using it, so I don't know. Yeah, I'm definitely missing a few people. Also, a reminder to people who have me for lab, remember, B group is next week, and that is the last physical face-to-face meeting of this semester. So bring whatever you have done, hopefully some back work, to turn in, and then the rest of it, which you do have a few more weeks to finish, but it's going to have to be scanned or take a picture, convert it to PDF, because the college is not doing any more face-to-face meetings after the Thanksgiving holiday, precautionary and all that. So be aware that that is part of what's going on also. There is one more Zoom lab that will be held for both Group A and Group B on the 7th of December. And we'll hold it at the normal time that lab is held, Monday at 5:30, but it will be Zoomed, and that way everybody can attend. It's what they call the Tinker Toy Lab. I have a set of molecular models that hopefully will prove a little bit helpful because I can like hold them up and show you a little bit more appropriately how some of the molecules are arranged in terms of their molecular geometry. Yeah, I really am blue. I'm not really sure what the deal is. All right, let me go back to electronic configuration, and I want to give you one more atom to look at, and I want to kind of go through it step by step. I created I popped open a different Word document because the whiteboard doesn't allow me to do upscripts and subscripts. So I'm trying to resolve that problem by using a separate whiteboard, if it will let me do this. Okay, where did my document go? Okay, that didn't work. Oh, there it is. Never mind, it's like hidden. All right, let me pick on tungsten. I wanted to pick on one that was biggish. So when you look at tungsten on the periodic table, tungsten is W, and it is number 74. This means that we need to do something with 74 separate electrons in order to write electronic configuration for it. Everything basically starts with the same spot. So we have 1s2 as the first part. So of my 74 electrons, the first 2 of them go in the 1s2. Remember that there are no P's or D's or F's in the first layer. So then my next layer has more than just S's in it, though. I have 2s2 and 2p6 because I want to fill up all the slots I have available. So if you add up your little upscripts, so I have 2n, 2n6, so that's 10 out of the 74. Now I'm also done with the second layer. Third layer comes next, and we do the 3s part of it first, and then the 3p part. So that's 8 more electrons there. But remember, the Aufbau starts to change its sort of logic pattern in terms of what you fill. This is why you need to use the little zigzaggy pattern that I embedded into your notes, because 3D doesn't come next. 3D is after 4s. So 4s2 is my next set there. So now I've got 2 and 2 and 6. That's 10, 12, 18. And I'm just going to kind of write this over to the side here. This is 20 electrons so far. I'm going to start a new line. You don't have to start a new line. I'm just trying to make it a little bit easier to read. So I've got 20 out of my 74 dealt with. Now I get to do D's, because after you have filled up your 4s, then the next segment is the 3D portion. So I can do 3D, and this one holds up to 10. So suddenly I've filled up quite a bit more. I've got 30 electrons accounted for. Okay. So this will get me all the way over to the 4p section then. So 4p6. Okay, so that's 20, 30, 36. And then we have 5s2. And then we kind of hit sort of what looks like weirdness again of 4D10. Okay. As you're using the periodic table, one of the things we'll talk about here in a moment is there's a pattern to the table that mimics the Aufbau pattern. And you have to kind of look at where you're going in terms of going across the rows, because it literally is not the same shell number. This is why we go from 5S2 to 4D10. Now I've lost count of what I'm doing here. All right, so 4D10, and then 5P comes next. So 5P6, and that gets me all the way to the end of that row. Well, yeah, row. And then 6S2. And then we have just a few left. Okay, this gets us all the way up to 56. Okay, and from 6S2, and then we're actually gonna hit some Fs. This is the very first time we actually hit F parts. And it's gotta be 4F. Oops. This guy's supposed to be an upscript. 4F14. Okay, that gets us all the way through there. And so we've got 20, 30, 36, 38, 48, 54, 56, and then all the way through the Fs. And that gets us all the way over to 70. And that should give me just 4 left then. So 5D. Oops, I'm sticking my subscript in the wrong spot there. All right. And providing I can count, that actually should be the right number of electrons then. So we've got 20 in the first row, and then we've got 30 for the 3D10, 36, 38, 48, 54, 56, 70, and the last 4. Okay, this is using the Aufbau. You have to always start at the beginning and you fill it up as many as you actually have electrons available. Now, I don't know if I can get my orbital notation thing to work here. If I do D's for orbital notation, I would have 5 blanks. Okay, because D's come in 5 pictures. Remember the pictures from last week? So if I have the pictures, each picture holds 2 electrons, and only 4 electrons are in the 5D segment. And I can't really draw arrows. I'm just going to kind of use number 1s because it'll at least make it kind of sort of look like arrows. So I've got basically 4 of my 5 slots have 1 electron in them. Over here on the far right hand side, my 5th blank has nothing. Also note, none of them have a buddy. None of them are paired. So I would say also, or I could say about this particular element, that it has 4 unpaired electrons. because the d orbital of the outside layer isn't full. Okay, it isn't full even halfway. I didn't even get to put anything in the fifth blank. All right, so why did it stop videoing? Okay, now my thing's not working at all. Hang on a second. Oh, great. Now it claims it can't detect a camera. Oh, there it is. Okay, now I'm blue again. All right, so think about your Aufbau. Make sure you are counting electrons and filling them up from the 1s all the way through until you run out of electrons. Hopefully that makes sense. I wish I had like a board to draw like Bilson was. I wish I had, I mean, I have a board, but I can't, it's hard to swap back and forth. So I'm kind of trying to jump around here.
So I got a quick question though, right?
Yes.
So when I'm looking at the pictures on in the notes, right? And
yes.
when you fill up the S's, so you got 1s, 2s, and 3 on that first section, right? So when you've done that, do we use the pictures and plus the that diagram, use them both together?
The pictures of the S's, the P's, the D's, and the F's are actually more for the purpose of teaching you why it's done a particular way.
Okay.
You're not drawing the pictures. You might be drawing lines, little dashes to put arrows in. If it asks you for orbital notation, but you're not drawing the pictures. You're not drawing the little loopy things, the balloons, the donut on a stick, or anything like that.
But when you started off with the 1s2, right?
Yes.
So those are, I'm trying to figure out where you got those from. You got those from, we better use the diagram or the
So let me pop open open the regular notes part and scroll back a little bit. If I can figure out where that is. Okay, so let me scroll back just a little bit. All right, so here is the undiagrammed part here. So if I kind of like highlight it and make it yellow. So that's the undiagrammed part,
okay,
which is not a different order from the diagrammed part, which has got all the little arrows in it, all the little like diagonal lines in it. Because if you follow this, you can go, you start at the bottom of each diagonal and go in the direction of the arrow. So 1s, 2s, 2p, 3s, 3p.
Oh, okay.
S.
So the arrow to the n equals 2. So I got
yes.
you. I got you.
Okay. It's the same order, but it's two different ways to present the information. Under more normal circumstances, usually this is a memory thing, and people use the diagonal thing as like the way to remember it. Obviously, you have notes for test usage, so you can either use the long string, the just straight up, the one that I had highlighted up here.
Okay.
The yellow one, or you can use the one with the diagonal lines. They're not different. Okay. They don't give you a different order. They both give you the same order. It's just a different way to kind of brain organize it.
Okay. And the max, and when you max them out, because
yes,
everything is times 2.
Yeah, fill up everything as much as you can until you get to the point where you are running out of electrons. So no more than 2s above your S, no more than 6 above your P's, no more than 10 above the D's, and no more than 14 above the F's. Each letter has a different max.
Gotcha. I see it. That's what's highlighted. I got you right here.
All
Okay.
right. So let me scroll kind of back down to where we sort of left off. I only devoted a couple of lines of the notes to this because I don't really love it, but it is mentioned in your textbook. I think they devote a page to it. There is, okay, I'll call it the shorthand method. It is also referred to as the noble gas notation. I do not love it because people tend to make mistakes in where they restart it. So for instance, I picked on manganese and I wrote it both ways here. There's the normal way. Okay, so manganese is one of the transition metals. It has 25 electrons. So I fill up my electron configuration. I've got the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and after that's 20. So the last 5 go in my 3D. But the way the noble gas notation works is you're supposed to look at your periodic table, figure out where the element is that you are seeking, and then backtrack, excuse me, backtrack to the closest before noble gas, and you put it in these little square brackets. And then you try to figure out, like for in this case, argon has 18 electrons. So if manganese has 25 electrons, using the argon is supposed to represent the fact that you have dealt with 18 of them. And then you have to figure out, well, how does that actually, how much of my Aufbau have I used up? And where am I supposed to start it again? The 18 being represented by the argon. So numbers 19 through 25, numbers 11 electrons, are the 4s2 and the 5d5. But it is error prone. People usually have a hard enough time trying to figure out how to do all the regular electronic configuration and keeping track of all your electrons. And suddenly now we're using something that deletes a whole bunch of them. And then you have to figure out where you're supposed to start up again. This is why I do not love this. Okay. It exists. Okay. I usually spend just a couple of minutes talking about it, but that's about it. Okay. It is not in your homework set, and I'm not going to ask test questions about it because I think it is more confusing than just going ahead and writing it out. People get lost too easily on where they're supposed to restart their electron count. All right, we do need to address valence electrons. And valence electrons are based upon everything that is not in the middle transition element section. So if you look at the list of columns there, note the columns that have hydrogen and beryllium, so they're on the left-hand side of your chunk in the middle of the table where all the transition elements are. Then there's boron all the way down through neon. Note, we're ignoring helium. Those are on the right-hand side of the transition elements. If you went and looked up what the configuration was for the things in those columns, you will notice that there is a great deal of similarity in the things that are in the same vertical column. We talked about the families way back in chapter 2. Now that kind of circles around to a little bit deeper of, well, there is actually a reason why, for instance, hydrogen, lithium, sodium, potassium, all those things that we dub dubbed alkali metals, like to be +1s. The reason being that every single one of the things in that column ends with an S1. Now, depending upon where you are going down the table, the number out in front changes 1 through 7, but they all end with an S1. Hence, this is why if you steal that one electron on the outside edge, you end up with +1 cations. So the numbers that we are paying specific attention to, like I said, we're right at the moment, we're ignoring all the transition elements. We're dealing with everything on kind of either side of that middle squash down segment of the table. So now I'm gonna have to switch again. I downloaded a different image. I think there's one similar to this in your textbook. Okay. So the left-hand 2 columns, they're sort of that pale blue color. Going from hydrogen all the way down to francium, you can kind of see a little more literally. 1s, 2s, 3s, 4s. Each time you go down a layer, you basically put one more number or advance the number that is in front of your S. Now look at the middle section. Scandium through zinc, yttrium through cadmium, lanthanum through mercury, actinium through meitnerium. And this is a slightly older table. It doesn't have the last couple on it, which are not super important. All of those, now note, even though the column that, or the column that has potassium in it, which is 4s1, if you go horizontally across the table, it doesn't go 4s4d because it follows the Aufbau. It goes 4s3d4p. So if you have a periodic table laying in front of you and you actually kind of understand the pattern, truthfully, you don't really actually need the Aufbau at all. You just have to understand that those 4 pink, we'll call them, rows there, 3D, 4D, 5D, and 6D, if it's an element from that segment, it's got to end in that section. Well, then we've got all the ones on the kind of right-hand chunk there. 2p, 3p, 4p, 5p, and 6p. Yes, helium is an exception because helium is so tiny. Helium doesn't have any p orbitals. It only has 1s2. So everything that is in that right-hand segment there, all of those have an electronic configuration that ends with some number and a p. And then we've got the weird ones at the bottom, the ones that we refer to as the lanthanum series and the actinide series. They're that weird kind of hyper purple color there. Because 4s and 5s are the only place you have f orbitals. 1, 2s, and 3s, there are no f's. And then, at least as far as we know, there are no 6f's either. You have 4f as an option, you have 5f as an option if you're in those particular elements, but no 6f's. So they refer to these as the block system. Okay, so left-hand two columns that are pale blue, that is your S block. The middle segment, where all the transition elements are, is referred to as the D block. The right-hand ones that are all kind of that shade of green, they are all P block. and the 2 purple rows down at the bottom are referred to as the F block. It's sort of an extra organizational tool. It helps you in looking at the periodic table kind of automatically make an estimate of, oh, well, I know I have to end my electronic configuration at basically this area. And it kind of helps with the organization there that way. I like the block system. I think it's a useful tool in the idea of kind of organizing your periodic table information. So let me flip back to regular note stuff. I will try to post a link to that particular image later, but I do think that there is the version of it in your textbook. It's not exactly the same, but it's close. So my little notes here that say S area, P area, all the transition metals are the ones that end with Ds. We call them the inner transition metals, also known as lanthanides and actinides, and those are the Fs. So now we're going to switch gears a little bit for the last hunk of the chapter. These are what is referred to as table trends. So the first one is atomic size, also sometimes referred to as atomic radii. How big is your atom? Well, once upon a time, pre-scanning tunneling microscopy and atomic force microscopy, the best they could do at that point in time was kind of ballpark having 2 atoms of the same element sitting next to each other, and then you kind of ballpark it based upon where you estimate the nuclei are, and this helps give us a radius. Because remember, in geometry, the radius is from the middle of the circle out to the edge. So the diatomic ones that are always diatomic, they're the easiest to measure by that method, but you can sort of fake it with other ones too. These days, they have a different methodology for measuring it. Radii are usually given in nanometers, although occasionally, if you're surfing the web, you may see them referred to in picometers or angstroms. Angstrom is something that's used an awful lot more in physics than it is in chemistry. It is 10 to the negative 10th meters. All right, let's look at the trend. Now, there is a table in your book that actually puts some numbers next to the pictures, but we're actually sort of focusing on the trend as kind of big picture idea. So look at the horizontal part of the trend. As you go from left to right, you are getting very slightly smaller. So if we look at, say, the second row, because the second row would actually start with lithium, and you look across the little dots there, you see, okay, the one on the left-hand side is the biggest one, and then we get a little smaller, all the way until we get to the right-hand side, and it's the smallest one. So what happens here is, now we go back to that whole thinking about layers thing. Everything in the same row is in the same layer. But if we add more protons, because remember, every time we jump one number on the periodic table, we add one more proton. One protons being positive, pull harder on the electrons if they are the same distance from the nucleus, because remember our layer idea. So as you're going toward the right, they pull a little bit harder each time. It's a less intuitive way to think about the whole way of arranging size than the vertical part of the trend. The vertical part of the trend makes more logical sense, just kind of like, oh, more electrons means bigger atom. Okay, that makes sense more automatically. So as you go down the periodic table, you have increasing size because you're jumping layers. We have 7 layers available, 1 at the top, 7 at the bottom. So every time you jump a row downward, you're adding a whole layer. So it makes lots of logic. And there's kind of sort of a reiteration here of what it says in the picture. What I did was I took my notes and I kind of left my notes alone and I embedded extra pictures in it to try to make it better visually. So there's kind of a duplication of explanations here. All right, next table trend. There are 5 total. 4 of them I will refer to as important table trends. And there is a 5th one, and I won't call it unimportant. I will just refer to it as less important. And we'll get to that shortly. Ionization energy. Energy required to remove an electron from a gaseous atom. Now think about that for a moment. We know that, especially up near the top of the periodic table, there's a batch of elements that occur in the gas phase just naturally. Oxygen, nitrogen, fluorine, chlorine, that kind of thing. But if we want to be able to compare them, we're actually going to heat them all up so that everything is in the same state of matter before we try to rip electrons off from it. Now, this table trend is a little bit different. Note, we have the left to right part of the trend is getting bigger. So the closer and closer and closer you get toward the corner where helium, fluorine, and neon are, the more energy it takes to steal electrons. The same is true going from the bottom toward the top. Okay, you will see some mentions in the textbook of first ionization energy and second ionization energy and sometimes third ionization energy. Numerically they differ, but the trends do not differ. All of the energies there have the same trend. Upper right-hand corner is high energy. Lower left-hand corner is low energy. All right, back to the whys. Layers make a difference. If you have few layers, hence helium, fluorine, neon, they've only got a couple of layers of electrons. If you are closer to the nucleus, and we already saw this in terms of size, the closer to the nucleus you are, the more pull there is between the positive of the protons and the negative of the electrons. They suck harder, okay? The protons are yanking down a lot harder on your electrons if they're closer. Now, that same proton idea also applies to the whole nuclear charge thing. If you've got fewer protons, even if you're in the same layer, and I picked on phosphorus and magnesium because they are both in the third layer of the atoms. Phosphorus is over in sort of toward the right-hand side there, so it's part of the P block. That's coincidental. Phosphorus has 15 protons because it's number 15 on the periodic table. Same layer, but with only 12 protons. 12 protons or 12 positives are not going to pull quite as hard as 15 positives. So the horizontal portion of this particular trend is super dependent on how many protons you have. But the vertical part of the trend is really more about how many layers you have in your atom. All right, now we get to the less important table trend. We're going to refer to this as electron affinity. And it's kind of sort of backwards of ionization energy. It's still all about gaseous atoms. But this one is about additions of electrons. And one of the reasons I will call this less important is adding electrons to metals, of which there are many, many, many metals, is in general more difficult than trying to add them to nonmetals. It has less uses. Okay, this is why I kind of categorize this one of the five as being sort of less important. There's less reasons to use it. I thought this was kind of an interesting visual. It was the best one I could find out, kind of to give you kind of an idea. If you look at it, obviously the green ones are taller. Okay, so you have bigger electron affinity, but it's sort of unpredictable. Okay, the up and down part is even more unpredictable. If you go like, up or down the periodic table, top to bottom. Okay, the left-hand ones, the purple ones, alkali metals, alkaline earth metals, okay, they're sort of predictable. But if you're looking at all the little boxes that are sort of drawn here for all those transition metals, yeah, there's a lot of unpredictability. All you can say is, in general, going from left to right, it takes more energy. That's kind of about the only statement you can make. So this is yet another sort of contributing reason as to why electron affinity has sort of less usefulness. All right, ionic radii. Now, dredge back in your brain, okay? Ions are charged. Cations are positive, anions are negative. Now we think about why that's true. Cations are positive because they lost electrons. The anions gained electrons. And I think I have the page number correct on this. If you looked at lithium, so lithium all by itself, all electrons intact, because 3 electrons, 3 protons, it's kind of a small atom to start with. It has a radius of 152. However, if I steal 1 electron, because it only had 1 electron in the second layer to start with, I've basically stolen an entire layer. My radius drops kind of dramatically. Lithium intact is the 152, but the lithium ion only has a radius of 78 picometers. So there's a pretty big difference there because I ripped off an entire layer. What usually tends to happen is, since anions are gaining electrons, they will give you larger things than neutral atoms, and the cations give you smaller ones. So there's this kind of weird split. Let me kind of scroll down here and have you look at pictures. The pictures are a little bit more obvious. Back to that whole idea of there are lots and lots and lots of metals. Everything that's blue is a metal. Everything that's green, actually, I guess actually it says the green ones are neutral atoms for references. So actually ignore the green ones. The red ones are all the ones that like to be anions. But you see that there's kind of this kind of weird split. If you look at all the blue ones, they go big stuff on the right, on the left-hand side, and then smaller, 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 smaller as you're going across. Then there's this giant jump. Because if you look at carbon as a cation, this is on the top row there. Carbon is a cation, and then nitrogen is an anion. Oh my God, there's a huge difference. Because carbon, you stole a whole bunch of its electrons. And in the nitrogen case, you added a bunch of electrons. It's still the same trend, though. The same trend is that for atomic size and ionic size, generally speaking, big trend, big stuff on the bottom, little stuff on the top. As a overall trend, big stuff on the left-hand side, smaller stuff on the right-hand side. But then you have to kind of throw in that little bit of a difference between the cations and the anions. Now we hit electronegativity. Now, electronegativity is actually probably of the five, whereas electron affinity is the least important of the table trends. Electronegativity is the most important, and it gets used a great deal, not only at the end of this chapter, it's going to bleed on into chapter 7 and also into the little smidge of chapter 8 that we will be doing. So kind of keep hold of information for electronegativity because it has lots of relevance. Now, all the other table trends are kind of a one atom at a time sort of thing. You look at the trend, you pick on an atom, you figure out where it goes in the trend. Electronegativity is more based upon reactivity. It's when the electrons are attracted to itself versus something else, which means usually it's part of a molecule. All right, let me scroll on down so I can show you the whole bit here. All right. In the world of electronegativity, fluorine is king, okay? Look over there on the right-hand corner, upper right-hand corner. It has the highest box, okay? Fluorine has the perfect score. It has a 4.0. Everything else is lower in comparison. Also note, there are no noble gases. Noble gases do not have, we'll call them measurable electronegativity because all of their slots in their electron configuration are full. Also note that there's a pattern to this. So if fluorine is king, its buddies that are close are also kind of high. We've got nitrogen and oxygen and chlorine. They're all red. They have fairly high electronegativity. Then you've got a fair number of yellow ones, especially all sort of still near that upper right-hand corner, but they're lower. Carbon, boron. But then look at the far left-hand corner. Hydrogen does not obey the rule. Hydrogen, if you were to draw it and like draw an arrow and put it where it fits in numerically, look at hydrogen's number. It's 2.1. So from an electronegativity point of view, hydrogen kind of snuggles down in between boron and carbon. It's the only one that doesn't really play in terms of this particular trend. You'll also see that there's a small number of transition metals down there kind of in the middle that are a little higher than you might expect them to be. Ruthenium, rhodium, palladium, osmium, iridium, platinum, and gold. Those have a little bit higher than you might expect based upon the rest of the trend. You'd think that maybe they should be green, like everything else kind of in that segment, but they're a little bit higher. We're not going to see a whole lot of them, though. A lot of times when we are looking at electronegativity, we're focusing fairly heavily on non-transition elements. So left-hand columns, alkali metals, alkali metals and alkaline earth metals, and then a whole bunch of the non-metals that are over there on the right-hand side. But all of this will come back again when we get to the next chapter in terms of helping you figure out bonding types. Bonding types are a stepping stone in all the things we're going to kind of have big picture stuff for the last couple of chapters of what does the molecule look like? How many electrons has it got? How are they arranged? What's the geometry look like? Is it polar? And what's its hybridization? So all of those are things that this kind of feeds into. So we start with the trend as kind of a base idea, and then later we build on that particular trend. That's why I'm kind of saying that electronegativity is sort of the most important of the five, whereas the electron affinity is the least important. So that is the end of this chapter. So homework is then due Thursday by midnight. I had a few people log in a little bit late. Since I have to go to DC for a medical appointment on Thursday, I'm going to Zoom from the hotel room, fingers crossed. Hopefully I will not have any hiccups and you can ask me questions about homework or whatever that night. And we'll probably do a little bit of chapter 7. Also probably end up talking about some more, a little bit more calculations for lab stuff too, because we are nearing the bitter end for lab. After the B group people have lab next week, then there's only one more lab, and it's a digital one. It's a Zoom one, which will be at same bat time, same bat channel, 5:30. Okay, on Mondays for everybody who has me for lab, just not in the lab. We're trying to avoid the whole having everybody come back to campus, because some people are traveling for Thanksgiving, some people are doing other things. So the college as a whole kind of went, yeah, we're gonna only do labs up until Thanksgiving, because there is lab next Monday. But after that, then no more. Questions? No questions? All right, so I will hopefully see you on Thursday and finish up your homework set for this chapter. Remember that the last test of the semester will include this chapter as well as chapter 7 and a little smidge of chapter 8.
You said you're gonna drop the lowest test that
Yes. Right at the moment, it does not show that way on Canvas because I actually have to have it display. Whoa. I have to have it display for test grades in order for me to be able to tell it to drop one, but that will happen at the end.
And
You are not allowed to drop,
you are
not allowed to drop the final exam. Okay, you can, if you choose to do so, you could drop the fourth test. I don't recommend it, but you could. But you are not allowed to drop the final exam. That is the required part.
And is the final exam online or are we
Yes.
going?
Yes, no, there's no,
Okay.
nobody is, like I said, no, as far as my understanding is that nobody is coming to campus. I'm not even sure that the professors are going to campus after Thanksgiving, not until January, after they've like deep cleaned everything again. The final exam will also be online. It will probably not be, I will probably give you a couple more hours to take it. Excuse me, I inhaled something. Instead of the 4-hour limit that I usually put on regular tests, I will probably do 6 for the final exam to give you a little extra time. It'll probably be 50 questions or 55 questions, thereabouts. It'll be a little bit longer and it's cumulative. It covers the whole semester.
Okay.
And I will talk more about that when we get closer to. I will give you some generalized tips on things to focus on for the final exam. Otherwise, I will hopefully, fingers crossed, see you on Thursday.